Good afternoon, this is Schweitzer, and run through a little video here on just the basics of titrations and how we can function and how calculations we can do with these things. So what can we do with the titration and how do we do it? Sort of the idea here. I don't have a note sheet for this at this point. We may have one in the future, but as of right now, we do not. So you can just take notes as you will. So can I determine the molarity of X beaker shown? Okay. Can I determine the molar mass of X shown? So this is some things that we're looking to do. So ultimately, through titration, we're looking to be able to gather moles from the titration, and from that, we can use the mass and the moles to get the molar mass, the gram per mole, or moles per liter to get the molarity. Two things that we're commonly trying to do. So in order to do this, in order to determine a known, or I should say an unknown, you must have a known to compare it to. So let's say, for example, we find a reaction. So how would we actually do this in this sense? There's a bunch of ways you could do it, chemically speaking. For example, I could convert X to something else, and maybe this something else has a property that I can monitor. And I know that, for example, I have 10 X's, and as I drop in Y's, X's are disappearing and O's are showing up, and I can track how many Y's I have to add in order to get all the X's to disappear. And if I know the quantity of X's, the quantity of Y's I add relative to how many X's I had here, and I know that they react in a 1-to-1 ratio, then I know that if I used 5 Y's, I also had 5 X's. This, of course, we're calling the equivalence point. Another way really would be to take something and add Y into it and cause Y to precipitate. Right? And then you can filter it out. We call this gravimetric analysis. And the first one we just call titration. And that is what we are more looking at. Now, this is not from an acid-base point of view, it's just from a general chemistry point of view. I'm dropping something in, hooking up to it with something else, and it's forming little O's. And then as I run out of X's and I make Y's, I could turn a different color, it could change properties, I could have a meter in here that's recording the change. Lots of things here. So in the end, though, I'm looking to equalize or come to the equivalence point of my Y's equaling my X's. In order to determine an unknown, I must have a known. This is considered my known. This is considered my unknown. I'm comparing the two by the Stoke ratio. So the objective of a titration: calculate the number of moles in a sample. And that's really what we're looking to do. What does the term equivalence mean? It means your moles are equal. So, for example, how do I use Y to determine X? Kind of alluded to this just momentarily ago, that I'm going to take and dump these in here. And if I know how many Y's I add 1 Y and knock out an X. Add another Y, knock out an X. Add another Y, and just keep knocking them out. And as I add more and more of them, eventually, maybe X is really purplish. And as soon as X is gone, it turns clear. And I'd note that it took 1, 2, 3, 4, 5 Y's to match the one. Well, there must have been 5 X's there to begin with. This is a pretty common example on a molecular level of how this works. Okay? This would be considered my known, and this would be considered my unknown. So when I have a common table that I use, it would be a known, unknown table. Now this is just a table, and it is molarity, moles, and liters. Now this is just not I made this up. Okay, so if you use this on a B test, they're just going to mark it wrong. They want work. It's just a data table. So if you know the molarity of this guy, and you know the volume with which you added, then you can calculate the moles And as long as the moles are equal, 5 and 5, then these are equal. And I'll use molarity times liters equals moles. Okay. All right. So let's try a real example here. It takes 10 milliliters of sample of vinegar, is titrated with known 0.5 molar HCl. It requires 20 milliliters of HCl to reach equivalence. Okay. What's the reaction taking place? Well, this is a neutralization reaction. So I could call this thing HX, for example, save myself some work. It's going to be, titrated with a known, because this is an acid, I'm going to change this over to NaOH, because we need a base. That's not going to work. All right, so it's going to be HX, which is this stuff, acetic acid vinegar, plus NaOH yields NaX plus H2O. Now the most important part here is that it's 1 to 1. One of these guys knocks out one of these guys. How many moles of base were used? Okay, so we'll switch these guys around, doesn't really matter. So our known is the molarity times liters equals moles. So this is the moles of my known. I'm kind of walking through the math for this guy right here. Make sure you show your work. Molarity is 0.5 times, the volume of 0.02 liters, and half of that is 0.01 moles. Now, because it's 1 to 1 ratio, this is also 0.01 moles. So the moles of they're equal. Okay, of your acid, in this case your NaOH, equaling your HX. What's the concentration of the vinegar? Well, I don't want the ending concentration. I want the original concentration. So when I dumped in of all these acids in here, HX, okay, and my volume's increasing, I'm dumping in hydroxides. I'm sort of neutralizing or destroying them as I go. And I don't want to know the ending concentration. I want the original concentration. So I want the original moles in the original volume. So originally, before I destroyed them, I had 0.01 moles of the acid in here. Now that's all gone. It's got neutralized. Now those original 0.01 moles were in the original volume of 10 milliliters. 0.01. And this is 1 molar. Okay. You should note that in my known unknown table, it would look like this. Known, unknown. What's known about the molarity is known. And the moles are equal. Okay, so this known is this guy, and sometimes I like to put a B above it and an A above it just to remind myself, but this is 0.5 and this is unknown. The volume is 0.02 liters or 20 milliliters. This guy is 0.01 or 10. Now, they're the same moles. So in this case, this guy has the same number of moles, but in half the volume, so it should be times 2. It should be twice as concentrated, which is 1 molar, and that is what I got. Okay. This is the most straightforward, simplest type of titration we can do. Okay. Well, they're all pretty decent. Okay, so I got 10 milliliters sample HCl is titrated with 0.01 molar NaOH. During titration, 15 milliliters of NaOH is required to reach solution. Okay, pause the video and try a couple of these problems and see if you can draw the pictures out. Alright, is the HCl more or less or equal concentrated compared to the base? Well, the moles are going to be equal. So let's look at our volumes. Okay, the unknown is in same number of moles, but in smaller volumes, so this guy's got increased concentration. So it's more concentrated because it's got same moles and less volume. What is the actual concentration? Okay, again, this is our known unknown table. I'm not going to use that because we've got a short work anyway. So it's going to be 0.1 times 0.015. That's my milliliters. This guy and that, make sure you line those two up and get the right numbers together. And this is going to be 0.0015 moles of my base, which equals the moles of my acid, too, at equivalence. Divide by the original volume of 0.01, and I will get my original concentration. So, 0.0015 divided by 0.01, and I get 0.15. And that should match up with my original idea that I would be more concentrated. Again, 15 and 10, you might not be able to do a linear relationship with that in your head, but you should understand that it's about a third bigger, and therefore it got a third bigger here. That makes sense. Complete the figures below after the following milliliters of base were added. Okay, 0. I'm going to use 4, so it's going to be HCl, so I'm going to draw HX, and this is going to be a strong acid, so I'll separate them, Cl minus. I'm just going to draw a dash for my chloride. So, H plus, H plus, H plus. 4 H pluses, as I indicate here. At 15 milliliters, let's do 7.5. So 7.5 is half of it. It's called that 1/2 equivalency. Half of it's gone. So we have all my anions are still there, and I've added in 2 hydroxides, 2 NaOHs, 2 of those. I've knocked out this guy and this guy. So there's my sodiums, and I have 2 waters. We might not even draw the waters, and then 2 H pluses still left over. In the end, okay, this is the equivalency point. Everything is gone at this point. I have 1, 2, 3, 4. All of my waters got knocked out. All my H pluses to waters. H2O, 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 and I've added in NaOHs to do that. I added in 4 of them, NaOH. So I would have technically 4 cations, 4 sodiums around here. Note that your positives and negatives always match. What happens if I add beyond that point? The only difference here is I add additional hydroxides to this thing, and therefore they have nothing to react with. So at this point, I'm just going to have some hydroxides left in that. This is the 17 milliliter beaker, and another cation. Okay. All right. How do you know when adding Y when you've reached equivalency? And this can be one of the more difficult things. I mean, this could be clear. Maybe X isn't showing up. So maybe it's got some sort of color, or maybe it's got nothing. So what we're going to do with this thing is use an indicator. An indicator is some chemical that wouldn't necessarily mess with anything, but just simply changes color and gives you changes color. Now, the most common or the most well-known one is phenolphthalein. Phenolphthalein is clear in acids and is pink, nice pink color in bases. Now, it's not perfect, and indicators are maybe nice for pools and stuff, but nowadays we pretty much can use a pH meter that would be really able to tell us. And we'll see some more coming forwards where we'll be able to drop a pH meter and just track the pH. And we'll see how that's going to work here in a moment. Okay. Phenolphthalein, very common chemical indicator. Of course, itself isn't going to change the reaction, just changes color. Alright, so tips and hints when setting up and running a titration. So we'll eventually have an opportunity, if you have not yet, to run a titration. A couple things that I would mention. One, we don't typically have to fill it to 0. You'll note that it says 0 up top even though it's full. That's because this thing is marking out the milliliters added. If you're at 0 and then you measure it, tells you how much you added. I also would mark out that even though it's, again, it doesn't matter, but if you're using a computer, then our tracking software works nice that if you start with 0, then when you add in, it just works nice with the computer to be able to know exactly how much you've added and tell the computer how much you've added. If you're not at 0, you could put 0 here, you would have an end and you'd have a change. So this is a manual way. Start could be 2.5, ends at 20, and therefore you have net difference is 19, 18, subtract here, 17.5 you added. The amount in the burette doesn't matter, it's how much you actually add And so a start-end change is a very common, just logistical thing in our notes that we're going to want to use. If you're using a pH meter, then we don't typically use one of those, and you'll see why momentarily. Again, I typically place the unknown in here. Unknown. And then here I put the known in. Again, it's not absolutely required, but just how I do it. And it tends to be pretty commonly done that way. The indicator also would go in here. You wouldn't want to put the indicator in the burette. Okay? So, and typically an indicator could be just a couple drops, but that would be something that I would also mention. Okay? This is called the stopcock or a valve, and it makes sure you understand which way it turns to be open, which way it turns to be closed. Alright, so what would a titration curve look like if we're using a pH meter? Okay, so we got a little pH meter here measuring the pH and shuffling it up to this computer, which is tracking the pH. What would titration curve look like? At 25 milliliters, 0.1 molar HCl is being titrated with 0.1 molar NaOH. So we should realize they're the same concentration. So I should require, how many milliliters should be required? 25 milliliters should be required. At equivalence, what is the pH? So this is going to be what it looks like. There it is. I'll just show here. So this is it. And you'll see right at 25 milliliters, it spikes and it starts to shoot straight up, and eventually just tag off like that. So that's what it looks like. And that answered this. What is the equivalence? What's the pH? Okay. Let's answer that question on the next one. What's the pH right here? It looks like it's pretty close to 7. Okay, let's draw out what it looks like. And I'm tracking H plus ions once again. Being able to model these things is really important. So I'm going to draw it out again and show you where I am on this thing so you can see it. I'm just going to draw 4 H pluses, H plus, H plus, H plus, and then 1, 2, 3, 4. That's located right here where nothing is added. Half equivalence point would be, well, if 15 is the equivalency, or 25, then 12 and a half would be the half equivalency. So now I've added enough hydroxide to knock out half of these guys. So I would typically just draw it like this, H plus, H plus. And you could draw it if you would like, just like that. Okay, the 4 anions, X negatives, are still there. And then at the equivalency point, right here, that's going to be 20, so this is going to be 12 and a half. This guy is 25, that's right there. And now, everything's gone. All I have left is my 4 cations and my 4 anions. And those guys are right here as well. You'll note here, HCl plus NaOH yields NaCl plus water. I don't always show the water because the whole beaker's water. This is a strong acid, strong base, so this is a neutral cation, neutral anion. So my pH at this point is going to be neutral because my salt is neutral. Alright. If I were to draw the point farther along at 28 milliliters maybe, then you should know it's just going to be cations and anions. But I'm going to be adding in more hydroxide. There's nothing, they don't have anything to react with, so they just pile up. Another cation, another hydroxide. That's how you want to show that. Notice the color of the indicator, that's my phenolphthalein. It turned from to red because it turned basic. Here it's clear, and then here it is pink. That's about the red color. Alright, so a little bit of practice here. We've got a little chart here showing this, and right away as you see this, you want to just drop this down and show, what does that show? It looks like 25 milliliters. So 15 milliliters of HF is titrated with 0.1 molar NaOH. What's the concentration of HF? Okay, so again, not that it's of that much use, but we typically, I shouldn't say typically, sometimes we'll use this, moles and liters. The known is 0.1. I put a base here, and I'll put my acid here. Okay, so this is my unknown, is my acid. My known's 0.1, and how much of my known did I add? That's the stuff that's in here. That's the stuff that's driving this up. This is the volume of my known. 25 milliliters. 0.25 or 0.025. Alright, so then at that point it says I got 15 milliliters of HF. Okay, unknown is my HF. I don't know the pH of it. And this is 15 milliliters, 0.015. A couple things I'll mention about this is that same moles, that my unknown is more concentrated than my known. Same moles in a smaller volume. Let's do the math here. Molarity times liters equals moles. 0.1 times 0.025 is 0.0025 moles. That's what goes right here and right here. And then 0.0025 moles divided by 0.015 gives me my new concentration. This is going to be 0.0025 divided by 0.015 is 0.16. 0.16 moles per liter. More concentrated than is my unknown, or my known. What is the pH at the equivalency point? Okay, so this is starting to get a little bit farther off here. Okay, so you should try this problem to see if you can do it. So at my equivalency point, I only have F negative. Okay, so this is my chemical reaction. I have HF plus OH negative yields F negative. And I'm just going to use moles here. I started out with 0.0025 of this and 0 of this. I added 0.0025 of that minus 0.0025 plus 0.0025. Now, because this is all I have left. You should be aware of that equals point. So, and we're going to be basic, by the way, because I only have my weak base. All right, so now I know I only have this stuff, none of that. So I'm going to use this equation. I have to use this equation. F negative plus H2O yields HF plus OH negative. Okay. Now, in this situation, where are we at? Initial stoichiometric ratio n. Now, 0.0025 divided by the new volume. That's going to go right here. Now, I had 15 milliliters of this thing, and I added another 25. So look, that's the total amount that's in my beaker here. That's what this stuff is sitting in. And that's 40 milliliters. So, 0.04 liters. And this is my new concentration of F negative. So it's going to be 0.0025 divided by 0.04 is 0.0625. 0.0625. Not playing a role. 0 minus x plus x plus x. At this point, the problem should be starting to look pretty familiar. X and x. We would use the Kb equals the concentration of the two products. Alright. HF and OH negative over F negative. Now, I only have the Ka, so I need to convert that to Kb. Kb is equal to Kw divided by Ka. Plug everything in, and now we get the Ka value. Kb value equals x squared over 0.0625. Note that this thing is using the shortcut rule. X will equal the concentration of hydroxides. Negative log of this thing will give you the P. Negative log of this concentration will give you the POH. And of course, we'd want to take 14 minus that value to give me my pH. And it should be basic. Alright, so a bunch of work there, but that's stuff we want to be able to do. Alright. One of these acids titrated as strong, one's weak. Which one's which? A couple of things you would note here. One, this one's got much lower pH, higher pH. This one looks like right in the middle is right near 7, if not right on 7. This one looks like middle right about there, which is about 9. So two things alone, starting point and here, indicates this thing is a weak. Now, one thing here again, because we have a weak base here, would indicate that this was a weak acid. That's important. This is neutral here, indicating this is a strong acid, plus the levels of pH. Alright, classroom practice here. A sample of acetic acid, 100 milliliters, 0.5, has a pH of 2.78. Write the hydrolysis equation. I'll pause the video and run all of these through here. Alright, hope you got a chance to try it out. Let's write out the hydrolysis equation. So it's an HC2H3O2 plus H2O yields H3O plus C2H3O2 negative. Write the expression. Okay, it's going to be Ka equals the concentration of H plus concentration of C2H3O2 negative over the concentration of HC2H3O2. Alright, now it says what's the Ka, so I need that guy. So to get this guy, as always, fill out the ice table. This guy is going to be 0.15, not playing a role, 0, 0, minus x plus x plus x, 0.15 minus x and x and x. Alright, so I need to fill a table up, but I don't have everything, so what do we got to do here? This 2.78 is going to fill it out, 10 to the negative 2.78. And this is going to give me my H plus concentration. Second log negative 2.78 and I get 0.00165. So X equals 0.00165 moles per liter. Alright, now you can just sub it all things in here and you can plug it in. It's going to be 0.00165 times 0.00165 over 0.15 minus 0.00165, and you can see that's not a whole lot different than that guy, and this is going to give you your Ka value. So your shortcut rule could be used here if you would like. And we're getting 1.8 e to the negative fifth. 1.8 e to the negative fifth. This is the Ka for this acid. Therefore, at the half equals point, when this guy equals this guy, this is a stronger acid than is the base. It's weaker. Equal concentrations at the half equals point would indicate that I'm still going to be acidic. At the equivalence point, I'm only going to have base, so I will be basic. Alright, take a moment, go ahead, give this one a try, and pause the video. Okay, so here we go. Let's try it. It says, determine the molar mass of an unknown acid. Now this is one where, okay, I want grams per mole. And the mass is going to be given to us. And I just need to find the moles via titration. So the grams is 0.5 located right here. 0.5 grams. Alright, and now really I'm just going to see if I use my known unknown table. Well, that's not as much of a use anymore. So let's go known, unknown, molarity, moles, liters. This guy is going to be known as my base, which is 0.1, 0.032, solving for the moles. That's molarity times liters equals moles. 0.1 times 0.032 is 0.0032, and that's my moles right here. And that's all I need. I don't need any of that. I don't need any of this. And I'm going to plug it in here. 0.0032 divide out. 0.5 divided by 0.0032 is 156 grams per mole. Okay. With that being said, that's a common, well, not as common as the molarity problem. And we'll stop there.